Section 6.3, Special Factoring. Alright, in this section we are going to take a look at a couple different forms of some odd looking expressions, some polynomials that aren't necessarily trinomials, although our first example will be, but we still can factor these things even though they're not trinomials, but they have to be a specific form, a kind of special form, and that's why we're calling it special factoring. So the first thing what we're going to look at is actually still a trinomial, but it's what we call a perfect square trinomial. Now, a perfect square trinomial is any trinomial, any three terms, that can be factored into the form x plus y times another parenthesis x plus y, or x minus y times another parenthesis x minus y. Really what that's saying is that you have the same two binomials, identical binomials, when you factor. So your two parentheses either have two terms being added and the same two terms being added in the second parenthesis, or they have the difference of two terms being subtracted. But either way, if you factor and you get the same two parenthesis factors, we call that original trinomial a special perfect square trinomial. Alright, so we'll look at this next example where it's not necessarily obvious that it was anything special, but we'll just try to factor it like we were doing in 6.2. We have a variable squared term, z squared. We have a single z term in the middle, and we have a constant on the end. So this is one of those forms of the trinomials that we can factor using the method where we find two numbers, two numbers that add to give us the b value, the number attached to z in this case, but those same two numbers have to be factors. They have to multiply to give us this number on the end, the 36. Okay? So we can find those two numbers, which are going to be -6 and -6. Okay? If we multiply -6 times -6, it gives us a positive 36, which we need. And then if we add a -6 plus -6, it gives us the -12 that we need for the middle term coefficient. So you can see our two factors are -6 and -6. This is when you have a perfect square trinomial, when you have the same two factors, two numbers that you find in this case. So if you remember from 6.2, how we write our factored form then is, we open up two parentheses, we have a z squared leading term, so we know we're going to have z and z there and there in order to get that z squared. And then we fill in our two factors we found, the -6 and the -6. And then going through and foiling that would get us back to the original expression, z squared minus 12z plus 36. But because when we factored we got two binomial factors that are the exact same thing, we can write this as z minus 6 squared. Okay? So that's why we call it a perfect square trinomial. We can factor it into some single expression squared, a perfect square. So other than knowing that that is a perfect square trinomial, there is a certain way to recognize from the beginning if your trinomial is going to be a perfect square. But I think it's just more work to try to memorize that kind of the way it will look, and it's easier just to factor it and see, do you get the same two binomial parentheses factors? And if you do get the same two, then you know it's a perfect square trinomial. Alright, so I think that's good enough for the perfect squares. Let's look at what we now call the difference of squares. This is going to look different than anything we've been factoring so far. So difference of squares is when we're going to have we only have two terms in our polynomial expression that we're trying to factor, and it has to be subtraction. So this is going to be, I think, a little bit obvious when it's this case, because you only have two terms and you have subtraction. You should kind of start to think this might be a difference of squares. I guess to define it a little more specifically, it's a difference of squares if the binomial, if we have the two terms, can be written as the difference, so subtracting something squared minus something else squared. So if we can think of our two terms that we're trying to factor as something squared minus something else squared, then it will factor into the sum of those two things that you are squaring, okay, adding them, multiplied by the difference of those two things you are squaring. So we're going to have the same two terms in both our parentheses, only one is going to be addition, one's going to be subtraction. Because when you FOIL this out, since we have opposite signs here of the two exact same things, we're going to get two middle terms that are identical except are opposite signs, and they cancel each other out. And that's why when if we were to FOIL something like this, we'd only get two terms. We wouldn't have that middle term. Okay? So I think looking at them will kind of define it a little better, if that's not making sense. So look at the first example. We have t squared minus 36. Okay? So we want to think, can we look at our two terms here as something squared and as something squared? In other words, are they square rootable? So t squared, can we think of this as something squared? Well, yeah, it already is written as something squared. Okay, we're taking the value t, whatever that is, and squaring it. Okay, so that's kind of the first check. 36, can we write that as something squared? Or in other words, is 36 square rootable? Well, yeah. 6 squared will get us 36. Okay? And then the last thing that needs to be the case for this to work, to factor the way we're looking, it has to be subtraction. It's the difference of two squares, not the sum of two squares. So all three of those things check. We have two terms that are squares. We have subtraction. Well, the way this formula works then, if we have something squared minus something else squared, we can factor it into a double parenthesis of the sum of the two things we are squaring, so adding the two things that were in parentheses over here and here, so t plus 6 multiplied by another matching factor, only subtraction, t minus 6. And again, FOILing that out would check, was how you can check to see if this is the correct factor, way to factor. T times t would give us t squared. T times negative 6 would give us a negative 6t. But then positive 6 times t will give us a positive 6t. So the negative 6t and the positive 6t will cancel out and would kill that middle term, the t term. Then lastly, 6 times negative 6 would give us the 6 times negative 6 would give us the negative 36. So that's why these expressions don't have that middle term, because when you factor them, they're opposites, and if you were to FOIL that out, it would cancel the middle term. Alright, slide this up. Let's look at our next few examples. So we have 16m squared minus 49p squared. So once again, because this is two terms and we're subtracting, you want to think about it as, well, this possibly could be a difference of squares. You just have to think of it, you have to think and determine, can I write 16m squared as some smaller term? You know, are we squaring? Could we write it as something squared to get 16m squared? So you could think, is there a number that squared will give you 16? And yeah, 4 squared gives you 16. And then what squared gives you m squared? Well, just a single m. If we square it, gives us the m squared. So if we take 4m times 4m, or in other words, if we square 4m, it gives us 16m squared. Okay. Minus, can we square root 49? Or in other words, is there a number that squares to give us 49? Yeah, 7. And then p squared, we already see that that's written as a square as well. So 7p is what we would have to be squaring in order to get 49p squared. 7p times 7p would give you 49p squared. Well, so that shows right there this is a difference of two squares. So it's going to factor into a double parenthesis of 4m plus 7p and another parenthesis of 4m minus 7p. Okay. And foiling that out would once again check to show that it does get you back to the original 16m squared minus 49p squared binomial. Alright. Next example, x to the fourth minus 1. This one doesn't necessarily look so obvious, but it is subtraction involved with two terms with a binomial. So you might, hopefully you see something like this and at least start to think of the idea that it could be a difference of squares. It's just a little trickier example of it. So first term, x to the fourth. Is there something we can square to get x to the fourth? Okay. Well, in fact, there is. Remembering our rules of exponents, if we take x squared to the second power, power to a power, well, x squared squared would give us x to the fourth. Alright, so x to the fourth, we could think of that it is a square. But what about 1? Is there something we could square in order to get 1? And yes, 1 squared gives us 1. So 1 is also a square, and we get 1 by squaring the number 1. So like I said, it's maybe not as obvious of a difference of squares situation, but it definitely is 1 now that we've broken it down this way. So we can factor this. Now that we see it's the difference of two squares, x squared plus 1 and x squared minus 1. Okay. Well, this is good. However, we can do more with this problem. If we look at our two parentheses that we now have, now that we factored, one of those might still be a difference of squares that we could factor using this method once again. And difference of squares, remember, has to be a difference, has to be subtraction. So this right here, where we're adding, this we would call the sum of squares. Okay, since we're adding two things that could be squared. That is not factorable. However, over here, we do have a difference of two terms, and it is a difference of squares, because x we could square. X squared is obviously a square, and we already just proved 1 is a square. So this still, what's left in that parenthesis, is still difference of squares. So that part of the answer will break down and factor into an x plus 1 times x minus 1. Okay, x and x to get you the x squared. 1 is a factor that, 1 times 1 will give you the 1. We need plus and minus because that's what's going to cancel out the middle term, and that's what leaves us with just x squared minus 1. Alright, so now we can write our final answer. Remember, this piece didn't factor. But then this piece did factor into these two. So we're going to end up with 3 parentheses. Okay. X squared plus 1, x plus 1 times x minus 1. Alright. And if we want, we could actually FOIL out these 2 parentheses, which would get us back to here. And then we would have to do the FOIL method with these 2 parentheses. And doing that, it would get us back to our original expression, x or x to the fourth minus 1. Alright, last example, we're asked to factor x squared plus 9. So, again, we want to look, do we have two terms that we can write as something being squared? X squared is clearly a square. Okay, we're squaring the variable x to get x squared. And 9 we can write as a square as well. Well, we're squaring 3. We would square 3 to get 9. So this looks like it is a difference of squares. However, we just talked about it up here. This is not a difference of squares. A difference of squares has to be subtraction. This would be considered a sum of squares. Which is not going to be factorable. Which, if you remember, the word for that we write is prime. Okay, if you try to mess around with factoring it and kind of FOIL it out, for example, you might think, okay, well, x plus 3 and x minus 3 then. Well, FOILing that, we will get the x squared. X times negative 3 will give us negative 3x. 3 times x would give us a positive 3x, so those are going to cancel in the middle. 3 and negative 3 gives us negative 9. So it's going to give us x squared minus 9. We have x squared plus 9. So that's not going to work. And if we made them both positive, okay, how would that change things? Well, making them both positive, we still have an x squared. Positive 3 plus positive 3 is going to give us a positive 9 at the end, but that's going to give us a 3x in the middle and another 3x in the middle, which is going to give us 6x. They don't cancel out, and we don't have a middle term here. So that way is not going to work. And even if we made these both minus when we were trying to factor, okay, that's still going to give us a positive 9 on the end when we multiply. Negative 3 times negative 3. X times x will give us the x squared, but it would give us two terms in the middle of a negative 3x and a negative 3x, which would combine to give us a minus 6x. So again, that doesn't cancel out the middle term like we would need it to. Okay? So that right there shows why it's not factorable. We just tried every possibility. Okay? So you don't want to write in all this. All you really need is to say that x squared plus 9, that expression, is prime. Okay, not factorable. And we'll finish the video here, and in the next video we'll look at the next page of the notes of 6.3, which is the sum and difference of cubes.